Hello everyone, my name is Neha Kartham and this is lecture 22 of Introduction to Automation. And in this lecture, we'll continue our discussion on AC motors. We'll be particularly looking at induction motors. Induction motors are widely used for their simplicity, reliability, and efficiency in converting electrical energy into mechanical motion. So let's explore about induction motor, its key principle and characteristics of these machines. Induction motor, it consists of rotor and a stator. The stator consists of stationary coils typically connected to a three-phase AC power source. When AC voltage is applied to the stator winding, it creates a rotating magnetic field. This rotating magnetic field induces an electromotive force in the rotor, causing it to rotate. Now, important thing to note is that in induction motor, it does not require any physical contact between the stator and the rotor for this process to occur, making it rugged and low maintenance. Induction motor can be classified into two types. First is squirrel cage, and the second one is wound rotor. The squirrel cage induction motors, they are most common and they are characterized by a rotor with conductive bars embedded in its core, whereas the wound rotor motors, they feature a rotor with windings connected to external resistors or rheostats, providing greater control over motor speed and torque. And one of the key advantages of induction motor is their ability to operate at almost constant speed under varying loads, a property which is called as slip. And this makes them ideal for application requiring consistent speed and torque, such as they are being used in pumps, fans, compressors, and conveyor systems. Now let's see the theory of operation. So the AC motors, they works by rotating the stator field, but it makes use of the natural alternating current of the AC wave to turn the field coils on and off sequentially. The AC induction motor does not need brushes because the rotor is essentially a passive device that is continuously being pulled in one direction. Now, to use an old analogy, we can say that a rotor basically behaves like a horse and the rotating stator field is the carrot. Now here, phase B, and this is phase A, and if we look at the waveform, we'll see that phase B is lagging behind the phase A by 90 degree. And that is, we can say that phase A peaks at 0 degree and phase B peaks at 90 degree later. The two-phase motors is connected so that the phase A energizes the top and bottom poles and phase B energizes the left and the right poles, these two poles. The action of two-phase AC on the motor is to cause the stator magnetic field to effectively rotate clockwise, even though the coils themselves are stationary. And the polarity of the applied voltage causes the top winding to present the north magnetic pole to the rotor, and the bottom one presents a south magnetic pole to the rotor. And this analysis it explains how the two-phase AC causes the magnetic field to act as if it were rotating in a clockwise direction. What was not apparent from this is from the discussion that I did is that the rotation of the field is smooth and it is continuous. It doesn't jump from pole to pole as might be evident from this picture also. So for example, let's consider a situation at 45 degree. In this waveform we can see from this waveform we see that both sets of the poles are energized at angle 45 degree. You can see phase 1 and phase B both are energized and causing the resultant north-south magnetic field to be halfway between the two poles. Now, the theory of operation is continued. So as I mentioned earlier, the rotating magnetic field generated by the stator completes one full revolution per cycle of the alternating current. For instance, at a line frequency of 60 Hz, the rotating field would achieve a speed of 3600 revolution per minute, which is calculated as 60 cycles per second multiplied by 60 seconds per minute, and that is equal to 3600 revolution per minute. And the speed of the rotating magnetic field is known as synchronous speed. It represents the ideal speed at which the rotor would rotate if it were able to keep pace with the rotating magnetic field. However, in reality, the rotor of an induction motor cannot achieve synchronous speed. This is due to the fact such as friction and slip. The rotor speed lags slightly behind the synchronous speed, and this discrepancy between the actual rotor speed and the synchronous speed is known as slip. Now, slip is essential for operation of the induction motor, as it creates the relative motion between the rotating magnetic field and the rotor, which is necessary for inducing current, and generating the torque. So we can say, in short, that while the rotating magnetic field of the induction motor operates at synchronous speed, the actual rotor speed is slightly lower due to the slip, and slip is a critical aspect of the motor's operation. Now we are going to look at one of the type of the induction motor, which is a squirrel cage induction motor. And in this, the rotor of the squirrel cage induction motor is constructed from a series of aluminum and copper bars connected by two end rings, and this distinctive configuration resembling a squirrel cage gives rise to the name of squirrel cage rotor. And unlike the traditional magnets, the squirrel cage rotor exhibits no inherent magnetic properties when the power is off. However, when alternating current power is applied to the stator windings and the stator field, and the stator field begins to rotate, the rotor, it undergoes a fascinating process of magnetization of induction. So let's see how it actually works. So as the rotating stator field passes by the individual bars of the rotor, the magnetic field strength in each bar fluctuates, and this changing magnetic field induces a voltage in the bars, and which basically prompt a current to flow through them. The current travels through the bars into the end rings and back through other bars, and that creates a magnetic field around the rotor. Now, this induced magnetic field interacts with the rotating stator field, which results in the mechanical torque, and the force that drives the mechanical torque, which is basically it's a force that drives the motion of the motor. So in some squirrel cage rotors feature bars embedded directly into the slots of a ferromagnetic core. It has a ferromagnetic core as shown in this figure. So in this design, no insulation separates the bar from the iron core, as the bar offers a significant lower resistance compared to the laminated iron sheets comprising of the core. And now next is so in this again squirrel cage motor is continued. So now in order for the squirrel cage motor to function effectively, a voltage must be induced from the stator to the rotor. However, this induction can only occur when there is a change in the magnetic field. For the rotor, this change occurs as a result of the rotating stator field passing by it. Now, here's what it gets interesting. Even though the rotor is constantly chasing the rotating stator field, it can never quite catch up the synchronous speed. And we discussed this earlier also in the couple of slides below before this. Why? Because if it did, if it catches up the synchronous speed, then what will happen? There would be no relative motion between the rotor and the stator, and consequently no induced voltage in the rotor. So this perpetual lagging behind the rotor compared to the rotating stator field is what we refer to as slip. Or in other words, we can say that slip is the difference in speed between the rotor and the rotating magnetic field of the stator. And slip is typically expressed as a percentage of synchronous speed, SS, that you see, and this is synchronous speed, and this is the rotor speed, SR. So it is a difference between them, and divided by the synchronous speed and multiplied by 100. So if multiplied by 100, then it is represented in a percentage. And in most cases, slip values for the squirrel cage motor, they are relatively low, typically less than 10%, which ensures efficient motor operation while maintaining the necessary relative motion between the rotor and the stator to induce the required voltage and generate mechanical torque. Now here comes the torque speed curve of an induction motor. So this torque speed curve, it's very useful for understanding the motor behavior. This curve shows torque available at various motor speed. So this is the speed, and here is the torque. So the maximum possible speed is 1800 RPM in this case for this particular graph. And this speed of the rotating stator field, and this is the synchronous speed. However, there is no torque at this speed because motor needs some slip to operate. To get the full load torque, a point defined by the manufacturer, the rotor must be slipping some. In this case, it is slipping at the reduced speed at 1725 RPM. So these motors, they have good speed regulation in operating range, and that is the speed changes little over wide range of the load torque demand. So we can notice in this figure that the AC motor behaves like something like DC motor in the operating range. That is, as the load increases, the speed also, as the load increases, the speed also decreases. However, at a certain point, which is called the pull-out torque here, as you can see. So at a pull-out torque, the torque drops off sharply, even though the speed is still decreasing. Okay. Now in real life, this means that if the load on the motor was increasing, the speed would decrease until the motor reaches the pull-out torque at this stage. So speed will still increase until it reaches the pull-out torque, at which this is the point at which the motor would quickly stall or would stop turning further, or the speed will reduce. So the starting torque that we see here will depend on the type of motor, but it's typically 1.5 times greater than the rated load, and unlike the DC motor, it is not the maximum torque available. Now this is the single phase AC motors, which is the most common form of power and is available almost everywhere. For this reason, the single phase motor is in wide use for domestic and the commercial purposes, and typically for application where it requires 1 or 2 horsepower. So the basic operation theory is the same as for the motor induction motor that we discussed before. So it operates on the same principle, but this motor has one major problem. It can't start itself. So we are going to learn next that how can we start the single phase motors, induction motors. So the most common way to start a single phase motor is to use a second set of windings, which is called the start winding. As you can see, this is the single phase induction motor, and it has a start winding which are only energized during the startup period, and in effect the motor temporarily becomes a two-phase motor which is self-starting. And this type of motor is known by the name split phase. The AC in the start winding, alternating current in the start winding, should ideally be 90-degree out of phase with the run winding. So it has a run winding also, so it should be 90-degree out of phase. The simple split phase motor, as you see here, relies on the fact that the start winding, which consists of a few turns of thin wires, has much less inductance and much more resistance than the run winding. And so it creates a phase shift with respect to the run winding. When motor is up to about 80% of the speed, a switch opens. This is a centrifugal switch, and this switch opens automatically and disconnect the start winding. The motor then continues running on the run winding. So the starting method provides about 40 to in between 40 to 50 degree of phase shift, which is enough to start the motor, but not enough to provide a lot of startup torque. So the main winding, which is the run winding, is designed for the operation of 75% of the synchronous speed or and above speed. So the main winding, this run winding design is in such a way that the current lags behind the line voltage, because the coils embedded in the steel stator naturally builds up the strong magnetic field, which slows the build-up of the current in the winding. And this relationship between the line voltage and the line current we can see in this figure. And so the start winding in this is not wound identically to the main, but it contains few turns of much smaller diameter wire than that of the main winding, and which I already mentioned. And but to add up this point, that it also requires to reduce the amount of start current which lags the voltage. And this can be seen through this phasor, this waveform diagram. When both windings are connected in parallel across the line, the main winding and the run winding and the start winding current will be out of phase, and that we can see here. This IM is the main winding current and IS is the starting winding current. So they are out of phase, as we can see. Now, here you can see the characteristics of the single phase induction motor, and these are some parameters: peak efficiency, power factor, static torque, noise and vibration, components, and other and cost characteristics, and corresponding to that these notes are given. Moving forward, so this is a single phase motor using a capacitor with a centrifugal switch. So in this, the change compared to the previous one is that in this we have a capacitor added to the circuit. Previously we just had the run winding and the start winding. Now we have the capacitor over here. So when motor is started, the centrifugal switch that you see, it closed, and the capacitor causes the current in the start winding to lead the current in the run winding. And once the motor starts running, the switch opens and the motor continues to operate. In single phase mode on the run winding. The capacitor start motor can achieve up to full 90-degree phase shift between the run ends, the start winding, and with the consequence of high starting torque. So in one design called permanent split capacitor motor, the start windings are permanently connected and eliminating the need of the centrifugal switch. And this design increases the torque of the motor and also simplifies the hardware and increases the reliability and improves the power factor. And this type of motor also run more quietly with less vibration. And here we can see the phasor diagram for this, and this is the waveform diagram. Now moving forward is the two capacitor induction motor. So this motor uses large value capacitor for starting and then switches to a lower value running capacitor. So two capacitor motors, they enjoy the same performance benefit as the permanent split capacitor motor that we saw earlier. In this, because the run capacitor introduces some phase shift which more closely approximates a rotating field. So all single phase motor that we have discussed so far will start off running in the same direction with each power up, and by reversing the polarity of one of the winding, the motor will start run in the opposite direction. Now this is the diagram for the three-phase motors, and three-phase motor is simpler and smaller than its single-phase counterparts, but it can be used only where three-phase power is available. Usually this is used in the industrial site, therefore motors tend to be more tend to be from 2 horsepower and up. And it has 3 sets of stator windings, as you can see over here, phase A, B and C, with each set of windings being powered by one of the phase voltage, and the natural timing sequence of the 3 individual phase voltage produces the rotating stator field that pulls the rotor around. And the rotor in the squirrel cage type induction motor, which we discussed earlier, it basically in that the motor is so simple that it self start and we just apply the power and it starts. And the three-phase motor, it can be wired to run in either direction by simply reversing any 2 of the 3 leads. For example, if the 3 motor terminal are connected to phase ABC, it turns clockwise. Then if the wires be connected in the B and C, if the B and C are reversed, then the motor will rotate in the anti-clockwise direction. Now this is a split phase motor driven with a single phase AC, and in this circuit we have this winding 1, winding 2, and this is the capacitor. So typically they are small and are used to move something back and forth, such as operating and closing a valve or raising and lowering a garage door. So the problem is that in the two-phase AC is not available directly from the power company, so it must be created usually from a single phase AC, and this adds up complexity to the system, but it does provide the opportunity to control the direction of the rotation of the motor, and hence its value as a back and forth type of actuator in the control system. Now here is the controlling direction of the split phase control motor. So the capacitor causes the current in the winding 2, as you can see here. So when it switch is connected, then the current will flow through the capacitor and through the winding 2, leads up to the line current in the winding 1 by almost 90 degree. And to change the direction of the rotation, the capacitor must be able to switch so that it is in series with the other winding. So now the switch is down position, which causes the line voltage to flow in this direction, and when the switch is in the up direction, that the direction of the current will flow in this direction, and it reverses the direction of the motor. So this causes the motor to rotate in the opposite direction. So this is clockwise and this is anti-clockwise. Now here is the AC servo motor. In this servo motor, it has a control winding and the main winding, which are so the main winding is connected to an AC source, usually to 120 volts AC, and the control winding the main winding is basically connected to the AC source of a 120 volt AC, and the control winding is driven by electronic circuit. It causes the phase to be either leading or lagging the main winding, and thereby controlling the motor direction. And also it sets the magnitude of the control winding voltage, which determines the speed. And typically the maximum control voltage winding voltage is about 35 volts AC, and if the control windings has 0 volts, the motor will coast to a stop, and even though the main winding is still connected to the line voltage, it will still stop. So this is different from a normal induction motor that will continue to run on a single phase. Now moving on. Now here is the AC servo motor torque speed curve, and in this this is a high slip high torque motor, and which is designed typically for control system, and it has a relatively linear torque speed curve. And as you can see, the maximum torque occurs when the speed is 0, when the speed is 0, and when the motor is running, the speed is inversely proportional to the load torque. So we can put it in another way: the lighter the load, the faster the motor runs. And this is very similar to the way a DC motor behaves. So this was about the AC servo motor, and this is the end of the lecture. Thank you so much for listening to me.